Imagine a campfire on a distant shore, its light a steady beacon in the encompassing darkness. You watch it for hours, for days, for years. It never changes. Then one day, it flickers. Not just a little, but a deep, dramatic dimming, as if something vast and dark has momentarily passed in front of it. Then it returns to its normal brightness, only to flicker again later, this time with a different pattern, a different depth. What could cause such a thing? What colossal shape is moving in the dark so far away? This isn't a campfire, this is a star, a sun much like our own, located nearly 1,500 light-years from Earth. And its strange, unpredictable behavior has captured the imagination of the world. We call it KICE 846285, or more affectionately, Tabby's star, named after the astronomer Tabitha Boyajian, who led the team that first studied its bizarre light curve. To understand why Tabby's star is so special, we have to go back to the mission that found it. NASA's Kepler Space Telescope was a revolutionary instrument with a simple yet profound purpose: to find out if planets like Earth are common or rare in our galaxy. For 4 years it stared relentlessly at a single patch of sky, a field containing over 150,000 stars. The technique Kepler used is called the transit method. It's elegant in its simplicity. If an orbit is aligned just right, a planet will pass directly in front of its star. When that happens, it blocks a tiny fraction of starlight, a small temporary dip. It's like detecting a mosquito flying in front of a searchlight from miles away. Kepler was a spectacular success. It revealed a galaxy teeming with worlds. We learned there is at least one planet for every star in the sky on average. Rocky planets, gas giants, super-Earths, worlds orbiting 2 suns. The data poured down from space, a torrent of information for astronomers and citizen scientists to sift through. When the planet hunters first saw the light curve from KIC 846285, it was immediately clear that this was no ordinary planet. Planetary transits are symmetrical, U-shaped. A planet is a sphere, so as it begins to cross the star, the light dims gradually, stays at a minimum while the planet is fully in front, then gradually returns to normal as it exits. But the signal from Tabby's star was anything but. Sharp, asymmetrical dips appeared. Some lasted for days, others for just a few hours. The pattern was chaotic, unpredictable. The most dramatic event in Kepler's data came around day 1500. The star's light dropped by 15%, then partially recovered, then plunged again, 22%. A 22% drop is immense. To block that much light would require an object covering nearly a quarter of the star. If it were one solid object, it'd need about 1,000 times Earth's area. It wasn't one mosquito in a searchlight. It looked like a dense, disorganized swarm. When confronted with a cosmic mystery, scientists rightly turn first to natural explanations. The principle of Occam's razor tells us not to invent extraordinary new phenomena when a simpler, known one will do. The leading natural hypothesis for Tabby's star involves comets. Lots and lots of comets. We know our solar system has the Oort cloud, a vast reservoir of icy bodies orbiting far beyond the planets. It's conceivable that in KIC 846285, a passing star or some other gravitational disturbance recently sent a massive swarm of comets hurtling inward. These colossal, irregular debris clouds could pass in front of the star, blocking significant amounts of light. However, the comet hypothesis has serious problems. We would expect the heated dust and gas to glow in infrared, but when we aimed infrared telescopes at Tabby's star, we didn't see the expected strong infrared excess. The missing thermal glow is a major challenge to the comet swarm model, forcing us to consider even more exotic natural scenarios. Or perhaps, something else. This is where the idea of an alien megastructure enters the conversation. Specifically, a concept known as a Dyson sphere, or more accurately, a Dyson swarm. First proposed by the physicist Freeman Dyson way back in the 1960s, it's really a thought experiment about the long-term energy needs of a very advanced technological civilization. You see, a civilization's energy consumption tends to grow over time. Eventually they might require more energy than their home planet can provide. The ultimate energy source in any star system is, of course, the star itself. Dyson argued that a sufficiently advanced civilization might begin to build structures in orbit to capture that energy directly. A more likely scenario is a Dyson swarm, a vast collection of enormous, independent solar collectors, habitats orbiting their parent star. This hypothesis is tantalizing because it seems to explain some of the strange features of Tabby's star. A swarm of massive, flat, artificial structures could block a huge amount of starlight, accounting for those deep 22% dips. The long-term dimming might even be explained by the ongoing construction of such a swarm, as a civilization gradually adds more and more collectors, slowly but surely obscuring their star from our view over the decades. Given the tantalizing, if remote, possibility that Tabby's star is home to an advanced civilization, another kind of search began. The search for extraterrestrial intelligence, or SETI, is the field dedicated to listening for such signals. Using large radio telescopes, SETI projects scan the skies for narrow-band signals, artificial beacons that stand out against the natural, chaotic noise of the cosmos. Nature produces broadband radio noise across all frequencies, kind of like static. A focused, narrow signal would be like a pure whistle in a storm, a clear sign of technology. Almost immediately after the mystery of Tabby's star became public, the world's premier radio telescopes were pointed in its direction. They scanned millions of radio channels, searching for any deliberate, intelligent signal emanating from the star system. The results of these initial searches were profound and sobering. After weeks of careful observation and data analysis, the conclusion was announced: silence. The star system was, at least in the radio frequencies we were listening to, perfectly quiet. So where does this leave us? The mystery of Tabby's star, KIC 8462852, is far from solved. We have a star that flickers and fades in ways we just cannot fully explain. We have natural hypotheses, a swarm of comets that fit some of the data, but not all of it. We also have an extraordinary hypothesis, an alien megastructure, which faces big observational challenges. The next chapter will be written by a new generation of telescopes. The James Webb Space Telescope is perfectly suited to study it in infrared. Future ground-based observatories will keep monitoring the star's brightness, waiting to catch the next big dimming event and analyze its light in real time. Each new piece of data is a potential key to unlocking the puzzle. Whether the final answer is a natural phenomenon we haven't yet conceived, or the first confirmed sign of extraterrestrial technology, the journey to find it is what truly matters. Tabby's star reminds us the universe is stranger than we imagine. It invites us to look up with curiosity and expectation. Out there in the vast, silent darkness, mysteries beckon us forward, promising new knowledge and perhaps a new understanding of our place. The watch continues.